Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Let your body settle into whatever position feels right. There's no rush. We have all the time we need. Where in the world are you watching from? A quiet bedroom where the stars might be visible through your window? A cozy corner where the day has finally released its hold? Wherever you are, you're exactly where you need to be. Tonight we're going to explore something that exists at the boundary between the everyday and the extraordinary. We'll talk about interstellar objects, visitors from beyond our solar system, carrying with them stories written in starlight and time. We'll discover what these cosmic travellers can tell us, what they mean for our understanding of the universe, and what keeps astronomers watching the sky with a mixture of wonder and careful attention. It's a journey that spans billions of miles and touches on some of the most profound questions we can ask about our place in the cosmos. But don't worry. This isn't going to be a story of alarm or fear. Instead, we'll move slowly and carefully through the science, the discovery, and the meaning of these distant visitors. We'll take our time with each idea, letting them settle naturally. By the end, I think you'll find a kind of peace in understanding both how vast the universe is and how carefully we're learning to read its signals. If you enjoy these calm explorations of the cosmos, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community. Your presence here means more than you know, so settle in. Let your shoulders drop away from your ears. Take a slow, deep breath and let it out even more slowly. And let's begin our slow drift through the story of visitors from beyond and the one scenario that made scientists pause and wonder. There's nowhere you need to be right now, nothing you need to solve. Just listen and let the story unfold like starlight reaching Earth after a journey of unimaginable distance. On October 19th, 2017, a telescope in Hawaii noticed something unusual. The Pan-STARRS Survey Telescope, designed to scan the sky for near-Earth objects, captured an image of what appeared to be an asteroid. But within days, astronomers realized they were looking at something they'd never seen before. Something that would change how we think about the space between stars. The object was moving fast, far faster than anything orbiting our sun should move. It was travelling at over 58,000 miles per hour relative to the Sun, and more importantly, it was on a hyperbolic trajectory. That's the technical way of saying it wasn't bound by our Sun's gravity. It had come from somewhere else, passed through our solar system like a stone skipping across a pond, and would continue on into the darkness beyond. They named it Oumuamua, a Hawaiian word meaning scout or messenger. It was the first confirmed interstellar object ever detected passing through our solar system. For the first time in human history, we had proof that objects travelled between the stars, and that we could detect them when they visited our small corner of the galaxy. What made Oumuamua particularly fascinating was its strangeness. Initial observations suggested it was shaped like a cigar or perhaps a pancake, tumbling end over end as it travelled. It was also accelerating slightly in a way that couldn't be explained by the sun's gravity alone. This led to speculation about its composition, its origin, and what it might tell us about planetary systems light years away from our own. The scientific community responded with careful excitement. Here was an actual sample of material from another star system, even if we could only observe it from a distance. Teams around the world pointed their telescopes at this cosmic visitor, gathering data on its brightness, its trajectory, its composition. Every measurement was precious because Oumuamua was already leaving, travelling away from the sun and back into the interstellar void at speeds we couldn't hope to match. But Oumuamua also taught us something important about our own limitations. By the time we realised what we were looking at, it was already past the inner solar system. We had only a brief window to study it before it became too faint for even our most powerful telescopes to detect. The visitor had come and gone, leaving us with more questions than answers, and with the certain knowledge that it wouldn't be the last. And this realization, gentle as it might seem, was profound. The space between stars wasn't empty. Objects travelled through it, perhaps in vast numbers, most of them invisible to us simply because we weren't looking in the right place at the right time. And if one interstellar object had found its way to us, there would be others. Which brings us naturally to the question of what we might find when we learn to look more carefully at the darkness between stars. Before Oumuamua, the idea of interstellar objects wasn't new. Scientists had theorized for decades that debris from other star systems should occasionally wander into ours. When stars form, when planets collide, when comets are flung from their home systems by gravitational interactions, some of that material has to end up travelling between the stars. The math suggested it. The physics supported it. But theory and confirmation are different things. The challenge wasn't just that space is vast, though it certainly is. The challenge was that interstellar objects are small, dark, and fast. They don't announce themselves. They don't glow on their own. We can only see them when sunlight bounces off their surface, and even then, only if we happen to be looking at the right patch of sky at the right moment. It's like trying to spot a single grain of sand thrown through a darkened warehouse, with only a flashlight to help you. Our detection methods had to become more sophisticated. Telescopes like pan-stars were designed to photograph the entire sky repeatedly, looking for anything that moved between images. Computers would compare millions of photographs, searching for the telltale signs of motion that indicated an asteroid, a comet, or something else. Most of what they found were familiar objects, rocks and ice balls native to our own solar system, following predictable orbits that had been established billions of years ago. But the software was also programmed to flag unusual trajectories, objects moving too fast or at odd angles or following paths that didn't match the expected orbital mechanics of our solar system. These flags needed human review, astronomers who could look at the data and determine whether they were seeing something genuinely unusual, or just a measurement error, a glitch, a cosmic false alarm. The detection of Oumuamua proved the system could work. It showed that with careful observation and quick follow-up, we could identify interstellar visitors while they were still close enough to study. This sparked a quiet revolution in how astronomers approach sky surveys. New programs were proposed, existing telescopes were given additional funding. The message was clear: if there was one interstellar object, there would be more. And we needed to be ready to find them. What astronomers discovered through modelling and simulation was both encouraging and humbling. Encouraging because their calculations suggested that interstellar objects might be relatively common, with several passing through the inner solar system every year. Humbling because most of them would remain undetected, too small or too faint or simply in the wrong part of the sky when we happened to be looking. We were, in effect, seeing only the tip of an enormous cosmic iceberg, one that extended throughout the galaxy in ways we were only beginning to understand. And so the search continued, with improved methods and heightened awareness. Astronomers knew they had missed countless visitors in the past, but now, with eyes trained and instruments ready, they watched the sky with renewed purpose, waiting for the next stranger to make its way through our neighbourhood. That wait wouldn't be long. On August 30th, 2019, an amateur astronomer named Gennady Borisov, working from his own observatory in Crimea, detected what he initially thought might be a comet. It was faint, barely visible even through his telescope, but there was something about its movement that caught his attention. He reported his finding to the Minor Planet Center, the organisation that tracks discoveries of asteroids and comets, and waited for confirmation. Within days, professional astronomers around the world had turned their instruments toward Borisov's discovery. What they found was remarkable. This wasn't just another comet. Like Oumuamua before it, this object was travelling on a hyperbolic trajectory. It had originated from outside our solar system, making it only the second confirmed interstellar object ever detected. They designated it 2I/Borisov, the underscore quote 0 underscore indicating it was the second interstellar object in our catalogue. But unlike Oumuamua, which had puzzled scientists with its unusual properties, 2I/Borisov appeared to be exactly what it looked like, a comet. It had a coma, that fuzzy cloud of gas and dust that surrounds a comet's nucleus when it gets close to the sun. It had a tail streaming behind it as solar radiation pushed dust particles away. In almost every measurable way, it behaved like the comets native to our own solar system. It was familiar, understandable, almost comforting in its normalcy. This familiarity told astronomers something important. The processes that form comets, the mixture of ice and rock and organic compounds, aren't unique to our solar system. They happen elsewhere, around other stars, in planetary systems that might be vastly different from our own in some ways, but share the same fundamental chemistry and physics. 2I/Borisov was proof that the universe operates by consistent rules, that what we see happening here happens in countless other places across the galaxy. Scientists made the most of this second opportunity. They measured 2I/Borisov's composition using spectroscopy, breaking down its light into component wavelengths to identify the chemicals present in its coma. They tracked its brightness as it approached the sun, reached perihelion, and began its journey back into interstellar space. They studied how it rotated, how it interacted with solar radiation, how its tail evolved over time. Every observation added to our understanding not just of this particular comet, but of comet formation in general. The timing of the discovery was also fortunate. Unlike Oumuamua, which was spotted as it was already leaving the solar system, 2I/Borisov was detected while it was still approaching. This gave astronomers months to study it, to coordinate observations between multiple telescopes and observatories, to build a comprehensive picture of this visitor from beyond. It was an opportunity they wouldn't waste, knowing that the next interstellar object might not arrive for months or years, and might not be so cooperative in revealing its secrets. As 2I/Borisov continued its journey, growing fainter as it moved away from the sun and back into the cold of interstellar space, it left behind something valuable: data. Terabytes of observations, measurements, spectra, images. This information would be studied for years, compared against theories and models, used to refine our understanding of what exists in the space between stars. And it raised a question that would occupy astronomers in the months and years that followed. What would the third interstellar object be like? Would it be another familiar comet, or something strange like Oumuamua? Or might it be something else entirely, something that would challenge our assumptions in ways we hadn't yet imagined? With 2 confirmed interstellar objects detected in just over 2 years, astronomers began to recognize patterns. They could now estimate, with reasonable confidence, how many interstellar objects might pass through the inner solar system in a given year. The numbers were larger than many had expected, perhaps a dozen objects larger than 100 meters across, and potentially thousands of smaller objects, all travelling through our cosmic neighbourhood at speeds that marked them as visitors rather than residents. This realisation led to the development of new search strategies. Telescopes began to focus not just on finding near-Earth asteroids, important as that work was for planetary defence, but also on detecting and characterising these interstellar visitors. The scientific community recognised that each detection was an opportunity to study material from another star system without the enormous expense and technical challenge of sending a spacecraft there. The Vera C. Rubin Observatory, a telescope being constructed in Chile, was particularly well suited for this task. Once operational, it would photograph the entire visible sky every few nights, creating a dynamic map of the heavens that would reveal anything that moved or changed. Simulation suggested it might detect dozens of interstellar objects every year, perhaps even hundreds, if they proved more common than current estimates suggested. This would transform the study of interstellar objects from a rare and exciting event into a systematic scientific endeavour. But there was also an element of uncertainty in all this. The 2 objects discovered so far, Oumuamua and 2I/Borisov, represented a sample size of 2. In statistics, That's not much to work with. Scientists could make educated guesses about what future discoveries might reveal, but they also knew that nature often surprises us. The universe is vast and ancient, and the processes that fling objects into interstellar space are varied and complex. There was no guarantee that the next visitor would fit neatly into our existing categories. Some astronomers began to think more carefully about what kinds of interstellar objects might exist. Comets and asteroids were the obvious candidates, the debris of planetary system formation and evolution. But what about larger objects? Could a planet, if gravitationally ejected from its home system, end up wandering between stars? Could fragments of destroyed planets shattered in collisions or torn apart by tidal forces travel the galaxy as interstellar debris? The possibilities were vast, limited only by the laws of physics and the creativity of cosmic processes. There was also the question of composition. Oumuamua had shown unusual properties that some scientists interpreted as evidence of exotic materials, though the mainstream explanation remained more conventional. But the incident raised awareness that interstellar objects might have compositions quite different from those common in our solar system. They came from different environments, formed around stars with different compositions, experienced different histories. Each one was potentially a unique sample of a distant world, carrying information that couldn't be obtained any other way. And so the astronomical community prepared itself, building the infrastructure to detect, track and study these cosmic visitors. They created protocols for rapid response, networks of telescopes that could quickly focus on newly discovered objects to gather maximum data before they faded from view. They refined their models, updated their estimates, published papers exploring the implications of an increasing catalogue of interstellar objects. The age of interstellar object astronomy had truly begun, and with it came both excitement and a sense of anticipation for what might be found next in the darkness between stars. To understand why some objects become interstellar travellers while others remain bound to their home star systems, we need to think about gravity and velocity. Every object in a planetary system is held in place by the gravitational pull of its star. To escape this pull entirely, an object must reach what's called escape velocity, a speed that depends on both the object's distance from the star and the star's mass. For Earth to escape the Sun's gravitational influence, it would need to reach about 42 kilometers per second relative to the Sun. That's fast, nearly 100,000 miles per hour. Earth, of course, isn't going anywhere. It orbits comfortably at about 30 kilometers per second, safely below escape velocity. But smaller objects like comets and asteroids can have their velocities changed dramatically by gravitational interactions with planets. Imagine a comet in a long elliptical orbit around the Sun. As it approaches the inner solar system, it might pass near Jupiter, that giant planet with gravity strong enough to reshape entire populations of small bodies. If the geometry is just right, Jupiter's gravity can act like a cosmic slingshot, accelerating the comet to speeds that exceed the Sun's escape velocity. The comet, which had been a member of our solar system for billions of years, is suddenly ejected, sent on a trajectory that will carry it into interstellar space. This process, called gravitational scattering, happens around every star with planets. It's a natural consequence of orbital mechanics and gravitational interactions. Over billions of years, star systems shed material into the galaxy, slowly but steadily populating interstellar space with rocks and ice and dust. Most of this material is small, pieces of asteroids broken in collisions, comets that spent too much time near their star and lost their icy exteriors, fragments of planets shattered in violent impacts. But the process isn't limited to small objects. Under the right circumstances, planets themselves can be ejected. If a star system has multiple gas giants in unstable orbits, their gravitational interactions can eventually send one or more of them into interstellar space. These rogue planets, as they're sometimes called, might outnumber stars in our galaxy. They would be nearly impossible to detect travelling through the darkness without a star to illuminate them, but they would be there nonetheless, silent wanderers in the cosmic void. The material travelling between stars carries with it a history. An ejected comet retains the chemical signature of its formation, the particular mixture of elements that characterized its home star system. An asteroid fragment might bear the scars of ancient collisions, craters and cracks that tell stories of violence and change. Even the trajectory, the path an object takes through space, contains information. By carefully measuring velocity and direction, astronomers can sometimes trace an interstellar object back to its region of origin, identifying the general area of the galaxy it came from. This is why each detection is valuable. Each interstellar visitor is a message in a bottle, carrying information from distant parts of the galaxy directly to us. We don't need to travel to other star systems to study their composition, their history, their nature. The galaxy, in its slow and patient way, delivers samples to our doorstep. All we need to do is notice them, study them, and learn to read the messages they carry. And as our ability to detect these objects improves, the messages become more frequent, the data more rich, and our understanding of the galaxy deepens in ways that would have been impossible just a few years ago. Which leads us to consider what might happen if one of these cosmic messages arrives carrying information we weren't expecting. The Asteroid Terrestrial Impact Last Alert System, known as ATLAS, consists of 4 telescopes spread across the globe, designed to scan the entire visible sky every night. Its primary mission is planetary defense, identifying asteroids that might pose a threat to Earth. But like other survey telescopes, ATLAS also detects comets, distant asteroids, and occasionally something more unusual. The system operates automatically, taking hundreds of images each night and processing them through sophisticated software that identifies moving objects. Most detections are routine, known asteroids following predictable orbits, or newly discovered objects that quickly reveal themselves to be ordinary members of our solar system. But the software is also trained to flag anomalies, objects whose motion or brightness don't fit expected patterns. On a hypothetical night, let's imagine ATLAS detecting something unusual. The initial images show a faint object moving at a velocity that seems too high for a bound orbit. The software flags it for human review. An astronomer working through the nightly batch of flagged objects notices the unusual trajectory and requests follow-up observations. Additional telescopes point toward the coordinates, gathering more precise measurements of position and velocity. Within 24 hours, the preliminary orbit determination is complete. The object is indeed on a hyperbolic trajectory. It's an interstellar visitor, the 3rd confirmed detection of its kind. The designation 3I/ATLAS is assigned, acknowledging both the discovery system and the object's interstellar origin. News spreads quickly through the astronomical community. Observing proposals are hurriedly written. Telescope time is rearranged to accommodate this unexpected opportunity. But as more data arrives, something becomes apparent. This object is different from the 2 previous interstellar visitors. It's larger, perhaps several kilometers across, significantly bigger than either Oumuamua or 2I/Borisov. It's also brighter than expected for its distance, suggesting either a highly reflective surface or possibly some kind of outgassing, releasing material that catches and scatters sunlight. And most notably, its trajectory will bring it surprisingly close to the inner solar system, closer than either of the previous interstellar objects came. Initial speculation focuses on what the object might be. Is it a comet, like 2I/Borisov, but simply larger and more active? Is it something like Oumuamua, an interstellar asteroid with unusual properties? Or might it be something else, something that doesn't fit neatly into our existing categories? The uncertainty itself isn't alarming. Every new discovery comes with uncertainties. But there's something about this one, about its size and trajectory and brightness, that makes astronomers pay particularly close attention. The object is still months away from its closest approach to the Sun. There's time to study it, to refine the orbit calculations, to gather spectroscopic data that might reveal its composition. But there's also a certain anticipation building in the scientific community. This isn't just another interesting detection. This is something that might tell us something fundamental about what exists in the space between stars, about what kinds of objects travel the galaxy, about what surprises the universe still holds for those patient enough to watch and careful enough to listen. When astronomers detect a new object, especially one on an unusual trajectory, one of their first tasks is to calculate its orbit with as much precision as possible. This isn't always easy. Early observations might come from only a few nights, providing limited data about the object's position and motion. The calculations produce what's called an orbital solution, a best guess at the object's path based on available information, along with an uncertainty range that indicates how confident the astronomers are in their calculations. For 3I/ATLAS, the initial orbital solution suggested a trajectory that would bring it within the orbit of Mars, possibly even closer. But the uncertainty range was large. The object might pass significantly farther away, or it might come closer. More observations would narrow this uncertainty, providing a clearer picture of where the object was actually headed. Astronomers requested additional telescope time, coordinating observations across multiple facilities to get the best possible data. As days passed and more measurements accumulated, the orbital solution began to converge. The uncertainty shrank, and the most likely trajectory became clearer. The news was both interesting and sobering. 3I/ATLAS would indeed pass through the inner solar system, and its closest approach to the Sun would bring it within the orbit of Earth. Not close enough to pose any collision risk, the calculations were clear on that point, but close enough to be studied in unprecedented detail for an interstellar object. The trajectory itself raised questions. Most interstellar objects, like Oumuamua and 2I/Borisov, pass through the solar system at angles that take them well away from the inner planets. The gravitational influence of the Sun bends their path slightly, but they generally enter from one direction and exit from another, following what mathematicians call a hyperbolic trajectory. Their interaction with our solar system is brief, measured in months rather than years. But 3I/ATLAS was different. Its trajectory suggested it would spend more time near the Sun, allowing for extended observation. This was scientifically valuable, providing opportunities to study the object over a longer period, to watch how it changed as solar radiation warmed its surface, to measure properties that would be impossible to determine from a more distant flyby. The astronomical community recognized this as a rare opportunity, perhaps a once-in-a-career chance to study an interstellar visitor in such detail. Yet there was also an element that made some scientists pause. The object's brightness continued to increase as it approached the Sun, increasing faster than models predicted. This could mean several things. Perhaps the object was more reflective than initially thought. Perhaps it was outgassing more vigorously, releasing material that formed a temporary atmosphere around it. Or perhaps there was something about its composition or structure that didn't match assumptions based on the comets and asteroids of our own solar system. The uncertainty wasn't alarming in itself. Science progresses through observations that don't quite match expectations. These discrepancies are opportunities to learn, to refine our models, to discover something new about how the universe works. But they also require careful monitoring and analysis. Astronomers began to coordinate more intensively, sharing data in real time, running simulations to explore possible explanations for the object's behaviour. The name 3I/ATLAS began to appear more frequently in scientific discussions, not as a source of fear, but as a subject of intense scientific interest and careful attention. And this careful attention would reveal something unexpected. Scientific understanding builds on models, simplified representations of reality that help us predict how things will behave. For comets and asteroids, these models are well established, refined over decades of observation and study. They tell us how brightness should change with distance from the Sun, how much outgassing to expect based on size and composition, how trajectories should respond to the sun's gravity and the pressure of solar radiation. When an object behaves differently than models predict, it doesn't necessarily mean something is wrong with the object. Often, it means something is incomplete or incorrect about the model. This is how science progresses. Observations that don't fit expectations push us to refine our understanding, to consider factors we hadn't accounted for, to develop more sophisticated explanations that better match reality. For 3I/ATLAS, the first anomaly noticed was that brightness variation. As the object approached the sun, it should have become brighter in a predictable way, following what's called an inverse square law. Objects appear brighter when they're closer, dimmer when they're farther away, and the mathematics of this relationship is straightforward. But 3I/ATLAS was brightening faster than this law predicted. Something else was contributing to its brightness. The obvious explanation was outgassing. Comets, when warmed by the sun, release gas and dust that forms a coma around them. This material is highly reflective, catching sunlight and making the comet appear much brighter than its solid nucleus alone would be. But spectroscopic observations of 3I/ATLAS showed an unusual composition. The signature of water, usually dominant in cometary comas, was weaker than expected. Instead, there were hints of more exotic compounds, molecules that typically sublimate at different temperatures than water ice. This led to discussions about the object's formation environment. Perhaps it came from a star system with a different composition than our own, richer in certain elements and poorer in others. Perhaps it formed farther from its host star than typical comets, in a colder environment where different ices could condense. Or perhaps it had a layered structure, with an outer shell of one composition covering an interior of something else entirely. Each hypothesis could explain some of the observations, but none fit perfectly. The second anomaly was more subtle, as 3I/ATLAS moved through space. Careful measurements of its trajectory showed a tiny but persistent deviation from the predicted path. This wasn't unusual in itself. Oumuamua had shown similar behaviour, which scientists attributed to outgassing creating a small rocket effect. But the direction and magnitude of the deviation for 3/ATLAS didn't match what outgassing models predicted. Something else was influencing its motion, something that existing models didn't fully capture. Astronomers proposed various explanations. Perhaps the object was rotating in an unusual way, causing outgassing to be directional rather than uniform. Perhaps there were active regions on its surface, areas where sublimation was more intense, creating asymmetric forces. Perhaps the object's shape was highly irregular, affecting how solar radiation pressure acted on it. Teams ran simulations, compared different scenarios, tried to find a configuration that would match all the observations simultaneously. What emerged from these intensive efforts wasn't alarm but fascination. 3I/ATLAS was teaching us something about the diversity of objects that travel between stars. It showed that our experience with solar system comets and asteroids, vast as it was, didn't fully prepare us for the range of possibilities that exist in the galaxy. Each interstellar visitor would likely challenge our assumptions in some way, forcing us to expand our understanding, to develop more flexible models that could accommodate objects formed in environments quite different from our own. The scientific community settled into a pattern of careful observation and analysis. Whatever 3I/ATLAS was, whatever explained its unusual properties, the answer would emerge from patient accumulation of data and thoughtful interpretation. There was no rush. The object would remain observable for months as it passed through the inner solar system, and perhaps most importantly, there was no indication that its unusual properties represented any kind of threat. It was simply different, unexpectedly so, and that difference was exactly what made it scientifically valuable. In the quiet hours of late-night work, when astronomers reviewed data and wrote observation reports, a different kind of conversation sometimes emerged. Not the formal discourse of scientific papers, but the speculative discussions that happen at the boundaries of what's known. One such discussion centered on a question that was both profound and slightly uncomfortable. Could an interstellar object ever be artificial? The idea wasn't new. For decades, scientists involved in the search for extraterrestrial intelligence had considered the possibility that we might one day detect an alien spacecraft passing through our solar system. The speeds required for interstellar travel were enormous, but not impossible. The challenges were enormous, but not insurmountable. If another civilization had developed the technology and motivation for interstellar exploration, there was no physical reason they couldn't have sent probes into the galaxy. When Oumuamua was discovered, with its unusual shape and unexpected acceleration, some scientists had briefly entertained this possibility before settling on more conventional explanations. The scientific consensus remained that Oumuamua was natural, a fragment of an exoplanet or a hydrogen iceberg, something exotic but ultimately explicable through natural processes. But the incident had established a framework for thinking about how we would recognize an artificial object if we encountered one. For 3I/ATLAS, the anomalies in its behavior triggered similar discussions, though mostly in informal settings. The unusual brightness pattern, the unexpected trajectory deviation, the peculiar composition, these could all be explained by natural processes. But they could also, if one chose to interpret them differently, be consistent with something artificial. Not a spacecraft in the traditional sense, perhaps, but maybe a probe, a monitoring device, something sent into the galaxy to observe or collect data. The scientific method requires extraordinary evidence for extraordinary claims. The claim that an object is artificial is certainly extraordinary, and the evidence for 3I/ATLAS being anything other than natural was far from extraordinary. It was merely puzzling, and puzzling data is normal in science. Most mysteries resolve into mundane explanations once enough information is gathered. The history of astronomy is full of seemingly anomalous observations that turned out to have perfectly ordinary causes. Yet the possibility, however remote, couldn't be entirely dismissed. Part of good science is maintaining appropriate skepticism without closing doors prematurely. Astronomers studying 3I/ATLAS included in their observation program some measurements that would be particularly useful if the object turned out to be artificial. Radio telescopes listened for any signals. Optical observations looked for signs of geometry too regular to be natural. Thermal measurements checked for waste heat that might indicate machinery. All these. Searches came up empty. 3I/ATLAS showed no signs of being anything other than a natural object, albeit an unusual one. No radio signals emerged from it. Its shape, as far as could be determined from light curves, appeared irregular in the way natural objects typically are. Its thermal signature matched what would be expected from solar heating of a dark surface, with no anomalous heat sources. The conclusion seemed clear. This was natural. However poorly it fit existing models, but the exercise itself was valuable. It established protocols and methods for distinguishing natural from artificial, if such a distinction ever became necessary. It showed that the scientific community could approach even exotic possibilities with appropriate rigor and openness. And it reminded everyone that the galaxy is vast, ancient, and full of things we don't yet understand. Most mysteries have natural explanations, but maintaining humility in the face of the unknown is part of good science. As 3I/ATLAS continued its journey through the inner solar system, the scientific focus returned to more conventional questions. What was this object made of? Where did it come from? What could it tell us about planetary system formation in other parts of the galaxy? These were the questions that would yield productive research, that would advance our understanding in meaningful ways. The speculation about artificiality faded back into the realm of late-night conversation, interesting but not central to the real work of understanding this cosmic visitor. Every photon of light that reaches us from an interstellar object carries information. The colour of that light tells us about the object's composition. The intensity tells us about its size and reflectivity. The way it changes over time tells us about rotation, outgassing, and surface properties. Astronomers have become sophisticated at extracting this information, at reading the messages encoded in starlight. Spectroscopy is perhaps the most powerful tool for this kind of analysis. When light passes through a prism or a diffraction grating, it spreads into a spectrum. A rainbow of wavelengths from red to violet and beyond. But this spectrum isn't smooth. It contains dark lines where specific wavelengths have been absorbed and bright lines where specific wavelengths have been emitted. Each element and molecule has a unique spectral fingerprint, a pattern of lines that identifies it as surely as human fingerprints identify individuals. For 3I/ATLAS, spectroscopic observations revealed a composition that was both familiar and strange. Water was present, but in lower abundance than typical solar system comets. There were signatures of carbon dioxide, carbon monoxide, and methane, all common in comets. But there were also hints of more exotic species, complex organic molecules that suggested either an unusual formation environment or perhaps processing by cosmic rays during its journey through interstellar space. The ratios of isotopes, different forms of the same element with different numbers of neutrons, provided another layer of information. These ratios vary depending on the conditions under which materials form. The deuterium to hydrogen ratio, for instance, depends on temperature and can indicate whether material formed close to a star or far away in the cold outer reaches of a planetary system. The carbon-12 to carbon-13 ratio carries information about stellar nucleosynthesis, about the particular mix of elements that characterize the star system where the object originated. For 3I/ATLAS, these isotopic ratios were slightly different from solar system averages, not dramatically so, but noticeably. This suggested formation around a star with a somewhat different composition than our Sun, perhaps a star that was slightly older and therefore enriched with heavier elements from previous generations of stellar evolution. Or perhaps a star that was slightly younger, formed from a cloud of gas and dust that hadn't fully mixed, creating local variations in composition. The object's reflectivity, measured across different wavelengths, suggested a surface that was darker than most asteroids, but not as dark as the darkest asteroids known. Perhaps it was covered in organic material, carbon-rich compounds that had been processed by radiation during its long journey through interstellar space. Or perhaps it had a layer of dust, fine particles created by impacts or outgassing, that absorbed light more effectively than solid rock. As astronomers compiled all this data, a picture began to emerge. 3I/ATLAS was likely a comet-like object, rich in volatiles but with an unusual composition compared to solar system comets. It had probably formed in the outer regions of another star system, been gravitationally ejected, and spent millions or tens of millions of years travelling through interstellar space before its chance encounter with our solar system. The journey had altered it, cosmic rays breaking down complex molecules on its surface, impacts from interstellar dust grains creating a thin layer of shock-processed material. But there were still mysteries. The unusual brightness behaviour, the unexpected trajectory perturbations, these didn't fully resolve even with detailed composition data. Perhaps the object had a complex internal structure, layers of different materials with different sublimation temperatures. Perhaps it was a contact binary, two objects touching or nearly touching, orbiting each other so slowly they appeared as a single object. Perhaps there were active regions on its surface that models hadn't correctly predicted. The work of interpretation would continue for years after the object's departure. Long after 3I/ATLAS had faded from view, astronomers would be analysing the data collected during its passage, writing papers, proposing explanations, building more sophisticated models. Each interstellar visitor added to our knowledge, helping us understand the diversity of objects in the galaxy and the processes that shaped them. And somewhere in that growing understanding was a deeper truth about our place in the cosmos, about the connections between all stellar systems, and about the ancient dance of matter and energy that fills the space between stars. Behind every astronomical discovery are people, individuals who chose to spend their careers pointing instruments at the sky, analysing data, trying to understand phenomena that occur at scales and distances beyond human intuition. For those studying 3I/ATLAS, the experience was both professionally significant and personally meaningful. They were witnessing something rare, possibly unique, and their observations would contribute to humanity's growing understanding of the galaxy. Dr. Sarah Chen, working at the Keck Observatory in Hawaii, remembered the night she first observed 3I/ATLAS through the telescope. The object appeared as a faint smudge of light, unremarkable to the eye, but the knowledge of what it represented made the observation profound. This light had travelled not just from the object itself, but from its origin in another star system, carrying information across distances that humans would never physically traverse in her lifetime, or perhaps ever. The technical work was demanding. Spectroscopic observations required precise instrument calibration. The object's motion meant the telescope had to track it carefully, adjusting constantly to keep it centered in the field of view. Weather was a constant concern. Clouds or turbulence could ruin an observation session, wasting precious telescope time that was always in short supply. Success required not just technical skill but patience, adaptability, and a certain resilience in the face of setbacks. But beyond the technical challenges was a deeper satisfaction. Dr. Chen had become an astronomer because of a childhood fascination with space, with the question of what existed beyond Earth, beyond the solar system. Now she was directly contributing to answering that question, gathering data that would reveal something about other worlds, other star systems, parts of the galaxy that were otherwise inaccessible. The work was difficult, sometimes frustrating but fundamentally meaningful in a way that transcended the everyday difficulties. Collaboration was essential. No single telescope, no single observatory, no single astronomer could fully characterize 3I/ATLAS. The object needed to be observed across multiple wavelengths, from radio waves to visible light to infrared. It needed to be tracked continuously, requiring coordination between observatories across different time zones. Data needed to be shared rapidly, allowing researchers to build on each other's findings, to adjust their observation strategies based on what others were discovering. Dr. Michael Torres, coordinating observations from the European Southern Observatory in Chile, found himself in constant communication with colleagues around the world. Time zones became irrelevant as the international astronomical community maintained a nearly continuous watch on 3I/ATLAS. Email exchanges happened at all hours. Preprint papers appeared on online repositories almost daily, sharing preliminary results and requesting feedback. It was chaotic but also exhilarating, a glimpse of how science works at its best, when a shared goal unites people across boundaries of nationality, language and culture. There were moments of frustration. Instrument malfunctions lost observation time. Weather patterns refused to cooperate. Preliminary results sometimes contradicted each other, requiring careful work to determine which measurements were accurate and which contained errors. Scientific progress isn't smooth or linear. It advances through trial and error, through mistakes corrected and hypotheses revised. The researchers studying 3I/ATLAS lived this reality daily, celebrating small victories and learning from setbacks. But there were also moments of beauty, seeing a spectrum for the first time, revealing the chemical composition of material from another star system, watching the light curve evolve as the object rotated, slowly revealing its shape and surface properties, correlating observations across different wavelengths, and seeing a coherent picture emerge from what had been confusion and uncertainty. These moments reminded everyone why they had become scientists, why they had chosen careers spent trying to understand the cosmos. News of 3I/ATLAS spread beyond the astronomical community, capturing public attention in a way that celestial events sometimes do. Major news outlets ran stories about the quote one. Science journalists explained what made the object interesting, translating technical details into language accessible to general audiences. Social media discussions range from educated curiosity to wild speculation, as people tried to understand what this discovery meant. The astronomers studying 3I/ATLAS found themselves thrust into an unfamiliar role, that of public explainers. Dr. Chen gave interviews to journalists, carefully emphasizing both what was known and what remained uncertain. She found herself navigating a delicate balance, trying to convey genuine scientific interest without feeding sensationalism, acknowledging mysteries while pushing back against unfounded speculation about artificial origins or threats to Earth. This public interest was valuable. In its way, it reminded funding agencies and policymakers that space science mattered to people, that discoveries beyond Earth captured imagination and inspired wonder. But it also came with challenges. Miscommunications happened. Headlines sometimes emphasize drama over accuracy. The careful hedging that scientists use when discussing uncertain data, the quote 2 and quote 3 and quote 4 got lost in translation, replaced by more definitive claims than the data supported. Educational institutions saw the object as an opportunity. Planetariums developed shows about interstellar objects. Science teachers used 3I/ATLAS as a current example in their classes, showing students that scientific discovery wasn't just something from history books, but an ongoing process happening in real time. Universities offered public lectures, packed auditoriums listening to astronomers explain what made this visitor from beyond so interesting. Amateur astronomers contributed too. With large enough telescopes and careful technique, it was possible for dedicated amateurs to observe 3I/ATLAS themselves, not just read about it. Online communities shared observations, techniques, and excitement. People pointed their backyard telescopes at specific coordinates and saw for themselves that faint point of the light, knowing they were looking at something that had travelled between the stars. The shared experience created a sense of connection, a reminder that astronomy isn't just for professionals, but for anyone curious about the sky. For children, 3I/ATLAS became the subject of school projects and bedtime stories. Parents field questions about where it came from, where it was going, whether it might contain aliens or treasures or answers to cosmic mysteries. These conversations, fumbling and uncertain as they often were, represented something important. The passing of wonder from one generation to the next, the continuation of humanity's long fascination with what lies beyond our immediate world. But the public attention also had to be managed carefully. When some of the anomalous observations emerged, when scientists admitted they didn't fully understand certain aspects of the object's behaviour, speculation intensified. Online forums buzzed with theories, some grounded in science, others completely divorced from reality. The astronomers found themselves repeatedly explaining that mystery doesn't equal conspiracy, that unexplained doesn't mean inexplicable, that science progresses precisely through encountering and resolving puzzles. Dr. Torres found this aspect of the experience surprisingly rewarding despite its challenges. He had always believed that science benefited from public engagement, that discoveries made with public funding should be communicated to the public. 3I/ATLAS provided an opportunity to demonstrate how science actually works, complete with uncertainties, disagreements, and gradual resolution. It showed that scientists are human, that they sometimes don't know the answer, that they work through problems collaboratively and incrementally. This transparency, he hoped, might build trust in science as a process rather than just accepting conclusions on authority. As the weeks passed and more data accumulated, the public attention gradually shifted from sensational speculation to genuine appreciation for the scientific process. People began to understand that 3I/ATLAS didn't need to be artificial or dangerous to be interesting. Its value lay in what it could teach us about the galaxy, about planetary system formation, about the diversity of objects that exist in the cosmos. The wonder wasn't diminished by natural explanations. If anything, understanding made it more profound. To fully appreciate 3I/ATLAS, it helps to place it in the longer history of humanity's relationship with objects in the sky. For most of human history, the heavens seemed unchanging, eternal, with only the sun, moon and planets wandering against the fixed backdrop of stars. Comets, when they appeared, were often seen as omens, their unexpected presence in the sky interpreted as signs of divine displeasure or impending catastrophe. Edmund Halley's work in the 17th century began to change this perspective. By studying historical records of comet sightings, Halley recognised that some apparent new comets were actually the same object returning periodically. He predicted that a comet seen in 1682 would return in 1758, and when it did, exactly as predicted, it demonstrated that comets obeyed natural laws, that their behaviour was predictable, that they were part of the natural order rather than supernatural phenomena. This was a profound shift in human understanding. The sky wasn't a realm of gods and omens, but a place governed by physics and mathematics, comprehensible through careful observation and analysis. Comets were no longer terrifying harbingers, but interesting objects worthy of study. The fear didn't disappear entirely, humans being susceptible to anxiety about things falling from the sky, but it was joined by curiosity and the desire to understand. The 20th century brought new levels of understanding. Spacecraft visited comets directly, analysing their composition, photographing their surfaces, even landing instruments on their nuclei. What emerged was a picture of comets as pristine samples of the early solar system. Collections of ice and dust that had remained largely unchanged since the planets formed 4.5 billion years ago. They were time capsules, repositories of information about the conditions and materials present when Earth itself was being assembled. The discovery of exoplanets, beginning in the 1990s, added another layer to this understanding. We learned that planetary systems were common, that most stars host planets, that the solar system wasn't unique or even particularly unusual. This raised natural questions about whether those other systems also had comets, whether they experienced the same processes of planetary formation and gravitational scattering that characterized our own history. Oumuamua provided the first definitive answer. Yes, other systems had small bodies. Yes, those bodies could be ejected into interstellar space. Yes, they occasionally wandered into neighbouring star systems. The theory had been confirmed by observation. What had been speculation became established fact. The galaxy was full of travelling debris, fragments of planets and comets that moved between stars, carrying with them information about their origins. Each interstellar visitor added to this understanding. 2I/Borisov showed that at least some interstellar comets were similar to solar system comets, suggesting common formation processes across different stellar environments. 3I/ATLAS, with its unusual properties, hinted at diversity, at the possibility that not all planetary systems produce the same types of objects, that conditions around other stars could create materials and structures quite different from what we were familiar with. This historical progression mattered because it showed how scientific understanding builds gradually, each generation adding to what previous generations discovered. The ancients noticed that celestial bodies moved in regular patterns. Medieval and Renaissance astronomers measured those patterns with increasing precision. Enlightenment scientists explained the patterns using laws of motion and gravity. Modern astronomers extended that understanding to objects beyond our solar system, to the galaxy, and beyond. 3I/ATLAS wasn't just an interesting object. It was part of this ongoing story of discovery and understanding. The people studying it were continuing work that stretched back centuries, standing on foundations built by countless others who had looked at the sky and asked questions. The specific details would differ, the technology would be unrecognizable to earlier astronomers, but the fundamental impulse to understand what we see, to find patterns in observations, to build comprehensive explanations for natural phenomena, that was timeless. And perhaps most importantly, this historical context provided perspective. Every generation of astronomers encountered mysteries, phenomena that didn't fit existing understanding, observations that seemed anomalous or inexplicable. And every generation found explanations, refined their models, expanded their understanding. The mysteries of 3I/ATLAS would likely resolve the same way, through patient observation and careful analysis, adding another chapter to the long story of humanity's effort to comprehend the cosmos. One of the deeper questions prompted by 3I/ATLAS was whether our solar system was typical. Do other star systems look like ours, with rocky planets close to the star and gas giants farther out? Do they have asteroid belts and comet reservoirs? Do they experience the same evolutionary processes that shaped our planetary neighbourhood over billions of years? The exoplanet discoveries had already shown that solar systems came in remarkable variety. Some had hot Jupiters, giant planets orbiting very close to their stars, closer than Mercury orbits our Sun. These couldn't have formed there. Gas giants need colder temperatures to accumulate their massive atmospheres. They must have migrated inward after formation, a process that would have disrupted any smaller planets in their path. Other systems had 6 planets larger than Earth, but smaller than Neptune, orbiting in compact configurations that would be unstable in our solar system. Some systems had multiple planets in resonance. Their orbital periods related by simple ratios that kept them in stable configurations despite their proximity. The diversity was stunning, suggesting that planet formation, while following consistent physical laws, could produce vastly different outcomes depending on initial conditions. This meant that the comets and asteroids ejected from those systems, the objects that became interstellar travellers, might also be quite different from what we see in our solar system. A system dominated by hot Jupiters might produce mostly rocky debris, as the giants would have scattered or consumed most of the icy material during their inward migration. A system with super-Earths might have extensive asteroid belts ground down by frequent collisions. A system that experienced late heavy bombardment, like ours did, might eject vast numbers of comets all at once. 3I/ATLAS, with its unusual composition and behaviour, might be evidence of this diversity. Perhaps it came from a system quite different from ours, where the mix of elements was different, where the temperature profile was different, where the gravitational dynamics played out differently. The fact that it didn't quite match our expectations might simply reflect our limited experience with only one planetary system's worth of local objects. This perspective was humbling. For all our sophisticated instruments and mathematical models, our understanding was still grounded in observations of one star system among hundreds of billions in the galaxy. We were like people who had only ever seen one type of ecosystem trying to understand all of biology. Samples from elsewhere, even if just passing through, were invaluable for revealing how much we didn't know. Some scientists began to think more carefully about categories. Were comets and asteroids truly distinct types of objects, or just endpoints of a continuum? Were the objects we called asteroids in our solar system representative of a universal category, or just the specific outcomes of our particular formation history? Each interstellar visitor provided a new data point, helping to answer these questions or sometimes complicating them in productive ways. The study of 3I/ATLAS also raised methodological questions. When observing an object from another star system, how much could we safely assume based on our knowledge of solar system objects? Which properties were likely universal, determined by fundamental physics and chemistry, and which might vary depending on local conditions? These questions didn't have easy answers, but asking them was important for developing a more sophisticated understanding of planetary systems in general. There was also something philosophical in this consideration of uniqueness. The Copernican principle, the idea that we don't occupy a special place in the universe, had been extended again and again. Earth wasn't the centre of the solar system. The solar system wasn't the centre of the galaxy. The galaxy wasn't the centre of the universe. Now, the principle extended to planetary system architecture itself. Our arrangement of planets, our population of comets and asteroids, our particular history of impacts and migrations. These weren't templates for how all systems looked, but just one example among many. 3I/ATLAS, in its strangeness, was teaching us about the breadth of possibilities. The galaxy wasn't uniform. Star systems weren't copies of each other. The diversity of outcomes from similar physical laws was vast, perhaps even greater than we had imagined. And this diversity was a kind of richness, a complexity that made the universe more interesting rather than more confusing. Each new discovery added texture to our understanding, showing that reality was more nuanced than our theories had suggested. As the study of 3I/ATLAS progressed, some scientists found themselves contemplating questions that had less to do with physics and more to do with philosophy. What were our responsibilities when observing something from beyond? If we suspected even remotely that an object might be artificial, did that change how we should approach it? These questions didn't have clear answers, but thinking about them was important for establishing frameworks that might be needed in the future. The first ethical consideration was simply about honesty in reporting. When scientists made unexpected observations, when data didn't fit models, when mysteries emerged, there was pressure from multiple directions. The media wanted definitive statements. Funding agencies wanted clear results. Even colleagues sometimes pushed for stronger claims than the data supported. Maintaining scientific integrity meant resisting these pressures, being clear about uncertainty, avoiding the temptation to oversell findings. For 3I/ATLAS, this meant acknowledging freely that some aspects of the object's behaviour weren't yet understood. It meant presenting hypotheses as hypotheses, not conclusions. It meant sharing data openly so others could analyse it independently. This transparency was sometimes frustrating for those who wanted simple answers, but it was necessary for maintaining trust in the scientific process. Another consideration was about stewardship of observations. Telescope time is precious, allocated through competitive processes. When an unusual object appeared, there was always a risk of overemphasizing it at the expense of other valuable research. The astronomical community had to balance the genuine scientific interest in 3I/ATLAS against the need to maintain other observation programs, to support diverse research, to not let a single exciting discovery monopolize resources. This balance was managed through discussion and consensus. Observing proposals were reviewed by committees who could weigh the scientific value of studying 3I/ATLAS against other proposed observations. Additional time was sometimes made available by adjusting schedules or extending observation runs. The community found ways to accommodate the unusual opportunity without completely disrupting ongoing research programs. There was also the question of how to communicate with the public. Scientists have a responsibility to share their findings, to explain what they're discovering and why it matters. But they also have a responsibility not to create unwarranted alarm, not to feed speculation that has no basis in evidence, not to allow their work to be misrepresented in ways that could cause harm. The astronomers studying 3I/ATLAS took this responsibility seriously. They gave interviews emphasizing the object's scientific value, while being clear it posed no danger. They pushed back against sensational headlines while respecting journalists' need for engaging stories. They participated in public outreach, answering questions at lectures and online forums, helping people understand both what was known and what remained mysterious. Some scientists wondered about longer-term implications. If interstellar objects were common, if dozens or hundreds would be detected in coming years, how should this change our approach to astronomy? Should there be an international protocol for responding to unusual detections? Should there be reserved telescope time specifically for following up on interstellar visitors? Should there be standards for data sharing to maximize scientific return from these fleeting opportunities? These questions led to discussions that extended beyond any single object. Professional societies began developing guidelines. International organizations considered coordination frameworks. The goal wasn't to create rigid bureaucracy, but to ensure that when the next unusual object appeared, the global astronomical community could respond effectively and equitably. There was even discussion about the future possibility of active investigation rather than passive observation. If an interstellar object was detected early enough, with a trajectory that allowed it, could a spacecraft be sent to study it more closely? The technical challenges would be enormous, but perhaps not insurmountable. Oumuamua had passed through before anyone seriously considered this possibility, but 2I/Borisov had prompted preliminary studies of what such a mission might require. 3I/ATLAS renewed these discussions, adding urgency and focus. But any such mission would raise its own ethical questions. What if contact with a spacecraft altered the object somehow? Contaminating it with Earth material? What if the object really was artificial, however unlikely, and contact was unwise or even dangerous? What protocols should govern how humanity approached something from beyond our solar system? These weren't just technical questions, but deeply ethical ones, requiring input from beyond the scientific community alone. As astronomers observed 3I/ATLAS, studied its spectrum, tracked its motion, calculated its origin, they were also thinking about these broader implications. Science doesn't exist in isolation. It's part of human culture, shaped by values and ethics, connected to how we see ourselves and our place in the universe. Each discovery, each observation, each mystery solved or revealed contributed not just to knowledge, but to the ongoing human project of understanding who we are and what our relationship to the cosmos might be. As 3I/ATLAS approached its closest point to the Sun, observation intensity reached its peak. This was the opportunity astronomers had been preparing for, when the object would be brightest, most active, most revealing of its properties. Telescopes around the world tracked it continuously, gathering data across all available wavelengths. The object's perihelion, its closest approach to the Sun, occurred at a distance slightly greater than Earth's orbit. This meant it never came close to Earth itself, dispelling any lingering public anxiety about collision risk. But it did mean that solar heating reached its maximum intensity, warming the object's surface, potentially triggering outgassing, revealing what lay beneath any outer crust that might have formed during its long journey through cold interstellar space. Observations showed that 3I/ATLAS did indeed become more active as it approached perihelion. The coma around it brightened significantly, and careful imaging revealed structure within the coma. Jets of material streaming from specific locations on the object's surface. These jets suggested active regions where sublimation was particularly intense, perhaps areas where fresher ice lay close to the surface or where fractures allowed subsurface material to escape. The brightness increase, which had puzzled astronomers earlier in the approach, now seemed to stabilize. The object was following a more predictable pattern, though still not matching solar system comet models precisely. The consensus explanation was that the unusual early behavior had been due to the sublimation of some exotic volatile, a compound that evaporated at lower temperatures than water ice. As the object warmed and this material was depleted from the surface, the behavior became more dominated by water ice sublimation, which followed more familiar patterns. Spectroscopic observations during perihelion passage were particularly valuable. The increased brightness meant better signal-to-noise ratios, allowing detection of fainter spectral features. Researchers identified additional organic molecules in the coma, complex carbon-based compounds that might have formed in the object's original planetary system, or perhaps been created by radiation processing during its interstellar journey. Each detection added to the chemical portrait of this visitor from beyond. The trajectory perturbation, that subtle deviation from the predicted path, also became easier to measure with the more precise position data available during perihelion passage. The direction and magnitude were consistent with a small rocket effect from outgassing, though the efficiency was somewhat higher than models predicted. This suggested the outgassing was more directional than uniform, perhaps due to the object's rotation orientation or surface geography. Dr. Chen, observing from Hawaii, found herself moved by the experience in ways she hadn't anticipated. She was watching something that had travelled for millions of years, that had formed around a star she would never see, that carried information from a place forever beyond human reach. And for a brief moment in cosmic time, it was here, close enough to study, revealing its secrets to anyone patient enough to look carefully. The privilege of that moment wasn't lost on her. The observing teams worked around the clock during this period. As Earth rotated, bringing different observatories into darkness, the watch was passed from one hemisphere to another. Data was shared in near real time, allowing researchers to adjust their strategies based on what others were finding. It was an immense coordinated effort, hundreds of scientists working toward a common goal, and the camaraderie that developed during this intensive period would last long after the object had faded from view. There were technical challenges that had to be overcome moment by moment. Clouds at one observatory meant quickly rearranging the schedule to prioritise other sites. Instrument issues required rapid troubleshooting. The object's position against the background stars moved significantly hour by hour, requiring constant updates to telescope pointing. But these challenges were met with skill and dedication, the teams drawing on deep reserves of expertise and problem-solving ability. As 3I/ATLAS reached perihelion and began its outward journey, the frantic pace of observation gradually eased. The critical data had been gathered. The object was now well characterized, its properties measured, its mysteries at least partially unravelled. There would be continued observations as it receded, tracking its fading brightness, watching how its activity declined as it moved back into the cold of space. But the peak had passed, the moment of closest approach complete, and with it came a sense of satisfaction at work well done. In the weeks following perihelion, as 3I/ATLAS began its journey back into interstellar space, the focus shifted from observation to analysis. Terabytes of data had been collected, images and spectra and timing measurements, all waiting to be processed, calibrated, analysed, interpreted. This was where the slower, more contemplative work of science happened, where raw observations were transformed into understanding. The first papers appeared on preprint servers within days of perihelion passage. These were preliminary analyses. Researchers eager to share their initial findings with the community. The papers described the object's orbit with high precision, characterized its size and shape as well as possible, from light curves and radar observations, presented spectroscopic detections of various molecules, and offered initial interpretations of what it all meant. Not all the papers agreed. This was normal and healthy in science. Different teams, using different instruments and analysis techniques, sometimes reached different conclusions. One group might interpret a spectral feature as indicating the presence of a particular molecule, while another group, using different modelling assumptions, might attribute the same feature to something else. These disagreements would be resolved through discussion, reanalysis, and sometimes additional observations. Dr. Torres found himself deep in the work of comparing different measurements to build a comprehensive picture. Spectroscopic data from optical telescopes needed to be combined with infrared observations from space-based instruments. Radio observations provided information about the object's surface properties and rotation rate. Radar measurements, bouncing signals off the object and analysing the returns, revealed details about its size and shape that couldn't be determined any other way. What emerged from this synthesis was a portrait of an object that was indeed unusual but not inexplicable. 3IA-TLAS appeared to be a comet-like body, several kilometres across, with an irregular shape suggesting it might be a contact binary, or at least have a highly non-spherical form. Its composition was similar to solar system comets, but with notable differences in the relative abundances of various ices and the concentration of complex organic molecules. The object's surface appeared to have a layered structure. An outer crust, darkened by radiation exposure and depleted of the most volatile compounds, covered fresher material beneath. As the object warmed approaching the sun, this crust fractured in places, allowing subsurface ices to reach the surface and sublimate, creating the observed jets and coma. The unusual early brightening had been due to a layer rich in carbon monoxide, or some similar volatile just beneath the surface, which evaporated at lower temperatures than water ice. The trajectory perturbation was explained by outgassing that was preferentially directed due to the object's rotation and the location of active regions. As material streamed off the surface, it imparted a small but measurable thrust, like a natural rocket engine. The efficiency was higher than typical for solar system comets, because of the particular geometry involved, but it wasn't anomalous once that geometry was properly accounted for. The isotopic ratios, those subtle differences in composition that had suggested formation around a different star, were confirmed and refined. 3I/ATLAS had indeed formed elsewhere, in a system with a slightly different metallicity than our own. This didn't tell researchers exactly where it came from. The galaxy is too large and the object's trajectory too uncertain for that, but it confirmed its extrasolar origin beyond any doubt. The age of the object's surface was estimated by measuring the degree of alteration from cosmic ray exposure. Material in interstellar space is constantly bombarded by high-energy particles, which break down complex molecules and create distinctive isotopic anomalies. By measuring these effects, researchers could estimate that 3I/ATLAS had been travelling through interstellar space for somewhere between 10 and 50 million years. It was ancient by human standards, but young in cosmic terms, a relatively recent ejection from its home system. All of this data, all of these measurements and analyses, were compiled into more comprehensive papers that would be submitted to peer-reviewed journals. These papers would go through a rigorous review process, with other experts critically examining the methods, questioning the conclusions, suggesting improvements. It would be months before the full scientific results were officially published, but the process had begun, and with it, the transformation of observations into established knowledge. Dr. Chen, writing her contribution to one of these papers, reflected on how the mystery had resolved. The anomalies that had made 3I/ATLAS seem so unusual at first had explanations, some of them subtle or unexpected, but all of them grounded in physics and chemistry. The object wasn't revolutionary in the sense of overturning established understanding, but it was evolutionary, adding nuance and detail to our knowledge of interstellar objects and planetary system diversity. That was how science usually progressed, through incremental advances rather than dramatic revelations. Numbers have a quality that can seem abstract, but in astronomy, they are anchors to reality. The precise measurements collected from 3I/ATLAS, when examined carefully, told stories that transcended the individual data points. These stories were about processes that played out over millions of years, about conditions in distant star systems, about the interconnected nature of the galaxy itself. The object's velocity relative to the local standard of rest, the average motion of stars in our region of the galaxy, was measured at roughly 45 kilometers per second. This was faster than many stars move, but well within the range of typical stellar velocities. It suggested that 3I/ATLAS had been ejected from its home system relatively recently in galactic terms, hadn't had time for multiple gravitational encounters with other stars to significantly alter its path. The eccentricity of its orbit within our solar system, a parameter describing how elongated its trajectory was, exceeded 1 by a comfortable margin. This was the mathematical signature of an unbound orbit, confirming beyond any doubt that the object was just passing through, would never return, would continue into interstellar space, carrying with it the energy and velocity of its encounter with our Sun. The precision of this measurement was remarkable. Uncertainties reduced to tiny fractions of a percent through months of careful tracking. The rotation period, determined by watching brightness variations as the object tumbled through space, was approximately 8 hours. This was slower than many asteroids, but not unusual for a comet, especially one that might be a loosely bound collection of smaller pieces rather than a single solid object. The rotation appeared to be complex, possibly tumbling around multiple axes, which would explain some of the irregular brightness variations that had been observed. The albedo, the fraction of sunlight reflected rather than absorbed, was measured at roughly 4%. This made 3I/ATLAS darker than coal, darker than most objects in our solar system, though not quite as dark as some of the most primitive asteroids. The low albedo was consistent with a surface covered in organic materials, carbon-rich compounds that had been processed by radiation during the object's long interstellar journey. Temperature measurements taken in the infrared showed surface temperatures that followed the expected pattern based on solar heating. There were no anomalous hotspots, no signs of internal heat sources, nothing to suggest anything other than passive solar heating and re-radiation. This definitively ruled out certain exotic hypotheses, confirming that whatever 3I/ATLAS was, it wasn't generating its own energy. The mass, estimated indirectly from the strength of outgassing and various modelling assumptions, was somewhere in the range of a few trillion kilograms. This made it roughly comparable to a small mountain on Earth, massive on human scales but tiny in cosmic terms. The density was estimated at roughly 1 gram per cubic centimetre, suggesting a loose, porous structure rather than solid rock. This was consistent with a comet-like composition, a mixture of ice and dust with lots of empty space between the particles. Each of these numbers constrained the possible explanations for what 3I/ATLAS was and where it came from. They eliminated certain hypotheses while supporting others. They connected this specific object to broader understanding of how planetary systems form, evolve, and exchange material with the interstellar medium. Numbers, precise and unambiguous, provided the foundation on which interpretation could be built. Dr. Torres, reviewing these measurements, marvelled at the precision modern astronomy had achieved. A century ago, detecting such an object at all would have been impossible. 50 years ago, only the crudest measurements of its orbit would have been feasible. Now, thanks to advanced instruments and analysis techniques, scientists could characterize an object millions of miles away in extraordinary detail, measuring properties that revealed its history and composition, connecting it to the broader story of galactic evolution. The numbers also revealed something about the frequency of such visits. Based on the detections of Oumuamua, 2I/Borisov, and now 3I/Atlas, astronomers could refine their statistical estimates of how many interstellar objects pass through the inner solar system each year. The best estimate suggested somewhere between 5 and 15 objects larger than a few hundred meters across, with many more smaller objects below current detection thresholds. The galaxy, it seemed, was quite good at producing and distributing debris. This had implications for planetary systems everywhere. If our solar system was typical, then every star with planets was constantly being visited by objects from other systems, a steady rain of material from elsewhere in the galaxy. Most of this material would pass through harmlessly, too small and too sparse to have any measurable effect. But occasionally, over billions of years, perhaps some of it would be captured, adding a small but real component of extrasolar material to planetary environments. The numbers told another story too, about the vastness of space and the rarity of detection. Even with improved survey systems and better analysis techniques, humanity was only detecting a tiny fraction of the interstellar objects passing through our neighbourhood. Most remained invisible, too small or too faint, or simply in the wrong part of the sky at the wrong time. For every 3 I/ATLAS detected and characterised, dozens or hundreds passed through unnoticed silent travellers in the cosmic dark. With a comprehensive dataset on 3 I/ATLAS's properties, astronomers could attempt to trace its origins. This was detective work of the most challenging kind, trying to reconstruct events that happened millions of years ago, light years away, based on indirect evidence and probabilistic reasoning. But it was also fascinating work, connecting this single object to the broader processes that shape galaxies. The starting point was the object's velocity and direction. By running its trajectory backward in time, accounting for the gravitational influence of the Sun and Jupiter and other massive solar system bodies, researchers could determine how 3 I/ATLAS had entered our region of space. The calculations showed it had come from the general direction of the constellation Centaurus, from a region of space containing thousands of stars. But this didn't identify a specific origin. The object's journey through interstellar space had likely lasted millions of years, during which time both it and its parent star had moved significantly. Stars orbit the galactic centre, their paths occasionally perturbed by gravitational interactions with other stars or giant molecular clouds. Tracing both the object and potential parent stars backward through time, accounting for all these effects, was extraordinarily difficult. The best approach was probabilistic. Researchers identified stars in roughly the right region of space that were of appropriate age and type to have planetary systems capable of producing comet-like objects. They then calculated the probability that each star could be the origin, based on its motion, age, and composition. What emerged wasn't a definitive answer, but a probability distribution, a list of candidate stars ranked by likelihood. The most probable origin was a G-type star, similar to our Sun, located about 300 light-years away. This star had a slightly higher metallicity than the Sun, meaning it was enriched in elements heavier than hydrogen and helium, which matched the isotopic measurements from 3 I/ATLAS. The star's motion through the galaxy was such that it could plausibly have ejected the object on a trajectory that would bring it to our solar system after millions of years of travel. But this was far from certain. The second most probable origin was a K-type star, smaller and cooler than the Sun, located in a slightly different direction. This star's metallicity was also consistent with the measurements, and its motion also made it a plausible source. There were dozens of other candidates with non-negligible probabilities. Definitively identifying the true origin would require additional data that simply didn't exist. This uncertainty wasn't a failure. It reflected the genuine difficulty of the problem. The galaxy is vast, containing hundreds of billions of stars, and the gravitational perturbations that objects experience over millions of years are complex and chaotic in the mathematical sense. Being able to narrow the possibilities to a few dozen candidate systems was actually an achievement, a demonstration of how far astronomical detective work had progressed. The modelling also revealed something about the ejection process itself. Based on the object's size and composition, it had likely been a member of a comet reservoir analogous to our solar system's Oort cloud, a vast spherical shell of icy bodies orbiting far from its parent star. Gravitational interactions, perhaps with a passing star or perhaps with a giant planet in its home system, had given it enough energy to escape entirely, sending it on an interstellar trajectory. This kind of ejection was probably common in young star systems, periods when planetary orbits were still settling, when massive planets might migrate significantly, when gravitational interactions were frequent and energetic. As star systems aged and stabilized, ejections would become rarer, but they would never stop entirely. Passing stars, though rare on human timescales, were common enough over billions of years to ensure a steady production of interstellar objects. Some researchers used 3I/ATLAS as a test case for more sophisticated origin tracing methods. Could machine learning algorithms be trained to identify likely parent stars based on measured properties? Could galactic orbit integration be improved to better account for uncertainty? Could statistical techniques distinguish between competing origin hypotheses? The answers were partial and tentative, but each incremental improvement would help with future objects, building a methodology for this new field of interstellar object archaeology. Dr. Chen thought about the philosophical implications of this work. Here was an object that had been part of another planetary system, had orbited a different star, had been ejected in a violent gravitational encounter, and spent millions of years travelling alone through the cold interstellar medium. And now it was passing through our solar system. Briefly illuminated by our sun, studied by creatures on a small planet who had developed the ability to understand its nature and history. The chain of events connecting 3I/ATLAS's formation to its detection was extraordinary, a cosmic story written in gravity and light. Late at night, in the quiet hours after observation sessions ended, when the formal scientific discussions gave way to more personal reflections, some of the astronomers studying 3I/ATLAS found themselves contemplating a question that had no technical answer. What did this all mean? The question could be interpreted in many ways. Scientifically, 3I/ATLAS meant an addition to our knowledge, a new data point in understanding planetary systems and interstellar objects. Professionally, it meant papers to write, conferences to attend, students to train on this fascinating example. But personally, the meaning went deeper, touching on why these individuals had become astronomers in the first place. Dr. Chen, sitting alone at her telescope one night after the object had faded below detection threshold, thought about connection. 3I/ATLAS physically connected our solar system to other parts of the galaxy, carrying material that had formed light years away. But it also connected her to colleagues around the world, to the long tradition of astronomical inquiry, to the future when other observers would detect other objects and build on the work her generation was doing. Science was, in this way, fundamentally about connection across time and space. Dr. Torres, writing code to analyse the spectroscopic data, reflected on the nature of exploration. Humanity would likely never physically travel to the stars, at least not in any foreseeable future. The distances were too vast, the challenges too severe. But through objects like 3I/ATLAS, the stars came to us, bringing samples, bringing information, bringing evidence of processes happening in regions we couldn't directly visit. This was a kind of exploration, different from sending spacecraft or landing on alien worlds, but no less real or valuable. A younger researcher, Dr. Amara Singh, working on her dissertation based partly on 3I/ATLAS observations, thought about impermanence. The object had been part of a planetary system for billions of years, stable and unremarkable. Then a single gravitational interaction had sent it into the void, transforming it from a resident to a wanderer. Eventually, trillions of years in the future, it might be captured by another star, joining a different system, beginning a new phase of existence, or it might wander forever, a permanent exile. Either way, its nature had been fundamentally changed by random chance, by being in the wrong place at the wrong time when a gravitational disturbance passed through. This randomness, this contingency, was simultaneously humbling and liberating. It suggested that cosmic events weren't predetermined, that chance played a genuine role in how the universe unfolded. It also suggested that meaning wasn't inherent in objects or events, but something conscious beings assigned to them. 3I/ATLAS had no awareness of its journey, no sense of being ejected or of visiting our solar system. But for the humans observing it, the event was profoundly meaningful, an opportunity to learn and wonder. Some found meaning in the collaborative nature of the work. Modern astronomy required cooperation across institutions, nations, and continents. No single person or even single institution could fully characterize an object like 3I/ATLAS. Success required sharing data, coordinating observations, building on each other's insights. The scientific method, at its best, was a collective human endeavour, transcending individual ambition in service of shared understanding. Others found meaning in the timescales involved. 3I/ATLAS's journey had lasted millions of years, a span incomprehensible in human terms. Yet here it was, briefly intersecting with human awareness, being observed and studied and understood by creatures whose lives spanned mere decades. This intersection of vastly different timescales felt significant. A reminder that the universe operated on scales far beyond human experience, but was nevertheless comprehensible to human intelligence. There was also something poignant about the transience of the observation. 3I/ATLAS would never return. It would continue its journey through the galaxy, eventually moving far beyond any possibility of detection, carrying with it the data it had revealed and the mysteries it had generated. The humans who observed it would age, retire, eventually die. Future generations would read about it in papers and books, but the direct experience of discovery, of watching a cosmic visitor pass through, belonged to this specific moment in time. Dr. Chen wondered if distant astronomers, orbiting some other star, might someday detect objects ejected from our solar system. Would they puzzle over the composition, trying to understand what kind of planetary system had produced such debris? Would they try to trace its origin, perhaps identifying our sun as a candidate source? Would they, in their own way, wonder about the existence of life around the star their visitor came from? These questions had no answers, but asking them felt important. They connected the specific scientific work to broader human concerns about meaning, purpose, and our place in the cosmos. Science provided data and explanations, but it didn't directly provide meaning. That required human interpretation, human reflection, human choice about what to value and why. 3I/ATLAS offered an opportunity for such reflection, a chance to think about what it meant to be conscious beings in a vast, ancient, complex universe. As 3I/ATLAS receded from the sun, moving back into the cold outer reaches of the solar system, observations became more difficult. The object grew fainter each night, requiring longer exposure times and more sensitive instruments. Eventually, even the largest telescopes would lose it against the background of distant stars and galaxies. The visitor would fade into invisibility, continuing its journey unobserved. The final observations had a quality of melancholy to them. Astronomers knew they were seeing the last data they would ever collect from this particular object. There would be no follow-up observations months or years later, no chance to verify surprising results or gather additional measurements. What had been collected was all there would ever be, a fixed data set that would be analysed and reanalysed but never expanded. Dr. Chen made one of the last observations, pointing the Keck telescope at coordinates where 3I/ATLAS should be, exposing for nearly an hour to gather enough light. The object appeared as the faintest of dots, barely distinguishable from background noise even in the processed image. She calculated that it would be undetectable within a few weeks, crossing below the threshold where even the most sensitive instruments could separate its faint signal from the cosmic background. There was something peaceful in this fading. The intensity of the observation campaign, the rushed analysis and quick publications, the public attention and media inquiries, all of that was ending. What remained was the slower work of thorough analysis, comprehensive interpretation, careful documentation. The object itself was leaving, but its legacy in data and understanding would persist. Other astronomers were already turning their attention forward, to the next potential detection. Surveys continued scanning the sky, flagging unusual trajectories. Statistical projections suggested another interstellar object might be detected within a year or two, perhaps sooner with improving technology. Each detection would add to the growing understanding, building a comprehensive picture of what travelled between stars. But there was also acknowledgement that 3I/ATLAS had been special. Its size, its trajectory through the inner solar system, its unusual properties, these had combined to make it particularly interesting and valuable for study. The next object might be smaller, fainter, less revealing, or it might pass through too quickly for detailed characterization, or it might be entirely ordinary, teaching less about diversity than confirming what was already suspected. This uncertainty was part of the nature of astronomy. Discoveries couldn't be scheduled or predicted. Nature provided what nature provided, and scientists worked with whatever opportunities arose. The skill was in being ready, in having instruments capable of responding, in maintaining the infrastructure and expertise to capitalize on unexpected chances for learning. As the observation campaigns wound down, there were informal gatherings, astronomers meeting in person or virtually to discuss what they'd learned, to coordinate final papers, to plan for future objects. These gatherings had a social quality that transcended pure science. Friendships had been formed or strengthened during the intense collaboration. Shared experiences created bonds that would last throughout careers. Dr. Torres, organising one such gathering, reflected on how astronomy was fundamentally a human endeavour. Yes, it studied the cosmos, examined objects light years away, dealt with timescales spanning billions of years. But it was done by people, with human motivations and relationships and emotions. The discovery of 3I/ATLAS would be remembered not just as a scientific event, but as a human experience, a time when hundreds of people around the world worked together toward a common goal, united by curiosity and wonder. The object itself, oblivious to the attention it had received, continued its journey. Its trajectory would carry it out past Neptune, beyond the Kuiper Belt, into the vast emptiness beyond our sun's influence. In a few thousand years, it would be farther from the sun than any human spacecraft had ever travelled. In a few million years, it might pass near another star, though the distances between stars are so vast that, quote, 7 in this context meant many trillions of miles. And perhaps, in some distant future, it would be captured, falling into orbit around a new star, becoming a resident of a different planetary system. Or perhaps it would wander forever, a permanent traveller, carrying with it the chemical signature of its origin and the cosmic ray damage accumulated during its journey. Either fate seemed equally plausible, equally fitting for an object that existed at the boundary between belonging and exile. The formal scientific legacy of 3/ATLAS would be measured in publications, papers that documented what had been learned and contributed to the permanent record of astronomical knowledge. In the months following the object's departure, these papers appeared with increasing frequency, each focusing on specific aspects of the observations and their interpretation. The first wave of papers had appeared quickly, preliminary results shared through preprint servers almost as soon as data was processed. These papers presented basic characterization, orbital parameters, brightness measurements, initial spectroscopic detections. They established the foundation that later, more detailed analyses would build on. Some of these preliminary papers would later be superseded by more comprehensive studies, but they served an important purpose in rapidly disseminating basic information to the community. The second wave came several months later, after more careful analysis and peer review. These papers presented detailed spectroscopic analyses, identifying additional molecules in the coma and discussing what they revealed about composition. They presented refined orbital determinations with precise measurements of the trajectory perturbation from outgassing. They compared 3I/ATLAS to other interstellar objects and to solar system comets, looking for patterns and differences. Dr. Chen's contribution focused on the unusual brightness behaviour observed during the approach phase. Her paper, co-authored with collaborators from several institutions, presented evidence that the early brightening had been due to the sublimation of carbon monoxide from a layer just beneath the surface crust. As this layer was exhausted, the behaviour transitioned to more typical water ice-dominated outgassing. The paper included detailed modelling showing how this layered structure could have formed and why it produced the observed brightness pattern. Dr. Torres led a paper on the origin analysis, presenting the probabilistic determination of candidate parent stars. This was careful work, acknowledging the uncertainties while still providing the best possible constraints on where 3I/ATLAS had come from. The paper included extensive supplementary material, tables of candidate stars with their properties and calculated probabilities, making the analysis transparent and reproducible. Young Dr. Singh's dissertation, completed in the months after 3I/ATLAS's departure, incorporated multiple aspects of the observations. She examined how the object's properties compared to populations of comets in our solar system, looking for statistical differences that might reveal something about planetary system diversity. She also contributed to models of interstellar object populations, using the 3 confirmed detections to constrain how many such objects existed and how often they visited the inner solar system. These papers would be read by other astronomers, cited in future work, incorporated into reviews and textbooks. They would form part of the permanent record of scientific understanding, available to anyone curious about what had been learned. The peer review process, sometimes frustrating with its demands for revision and clarification, helped ensure that the published results met standards for rigour and accuracy. But beyond individual papers, 3I/ATLAS contributed to something larger, a growing framework for understanding interstellar objects as a population. Each new detection added to this framework, refining estimates, testing predictions, revealing patterns. With only 3 confirmed interstellar objects, the statistical basis was still weak, but it was growing, and with planned improvements in survey capabilities, it would grow more robust in coming years. The legacy also extended beyond traditional publications. Observational data from 3I/ATLAS was archived and made publicly available, allowing anyone with appropriate skills to analyse it. This data would be used not just for immediate studies but for future work, as techniques improved and new questions arose. Someone analysing data a decade or 2 later might discover something that initial observers had missed, adding new insights long after the object itself had faded from view. Educational materials were another part of the legacy. Teachers incorporated 3I/ATLAS into lessons about the solar system, interstellar space, and scientific discovery. Students used it as the subject of projects and reports. Planetariums updated their shows. Popular science books and articles described the discovery and what it meant. All of this contributed to public scientific literacy, helping people understand both the specific findings and the broader process of how science works. Perhaps most importantly, 3I/ATLAS had demonstrated the value of being prepared. The surveys that detected it, the rapid response protocols that allowed quick characterization, the international cooperation that enabled comprehensive observations, all of these had proven their worth. This would strengthen arguments for continued funding and development of capabilities to detect and study interstellar visitors. The investment in infrastructure and expertise had paid off, and that success made future investment more likely. With the immediate work complete and the object itself beyond reach, some researchers found themselves drawn back to broader questions that had no empirical answers but were worth contemplating nonetheless. These were questions about meaning and significance, about humanity's place in the cosmos, about what it meant to study something from beyond our immediate neighbourhood. One such question concerned the nature of exploration. Humanity had always been an exploring species, venturing beyond familiar territories, seeking to understand distant lands and peoples. Space had extended this impulse, first to nearby space with satellites and moon landings, then to the solar system with robotic probes. But the stars remained unreachable, too distant for any realistic near-term technology. Interstellar objects like 3I/ATLAS offered a different kind of exploration, where the distant came to us rather than us going to the distant. This inversion of the usual pattern raised philosophical questions about agency and discovery. Were we truly exploring if we were passive receivers of whatever happened to pass our way? Or was the act of observation and understanding itself a form of exploration, even if we couldn't choose our destinations? Some argued that the distinction was artificial. Exploration had always involved an element of chance, of stumbling upon the unexpected, of finding things you weren't specifically looking for. The Pacific voyagers who discovered new islands weren't always searching for those particular places. Antarctic explorers encountered phenomena they hadn't anticipated. Even planetary probes frequently made their most interesting discoveries through serendipity rather than careful planning. In this light, the chance arrival of interstellar objects fit comfortably within the broader pattern of exploration. Another question concerned the value of knowledge for its own sake. 3I/ATLAS wouldn't lead to practical applications, at least not directly. Understanding its composition and origin didn't solve immediate human problems. The resources devoted to studying it could, in principle, have been used for other purposes. Yet few astronomers questioned whether the study had been worthwhile. There was intrinsic value in understanding, in knowing, in satisfying curiosity about what existed beyond our immediate experience. This philosophical position, that knowledge was valuable independent of utility, had deep roots in human culture. It was reflected in art, literature, philosophy, and science itself. The question was whether it would continue to be culturally supported in an era of increasing resource constraints and practical challenges. The answer wasn't certain, but the widespread public interest in 3I/ATLAS suggested that curiosity about the cosmos remained a powerful human motivation. Dr. Torres found himself thinking about perspective. Astronomy had a unique ability to shift human perspective, to make people think about scales of time and space that dwarfed individual concerns. An object that had travelled millions of years, that came from hundreds of light years away, that would continue travelling long after human civilization had risen and fallen. This provided a cosmic context that could be simultaneously humbling and comforting. Humbling because it emphasized human insignificance in the vast scope of the universe. We were tiny creatures on a small planet, studying an equally tiny piece of debris from an unknown origin. Our existence was fleeting on cosmic timescales, our sphere of influence microscopic compared to galactic scales. But comforting too, because this cosmic perspective revealed that the concerns and anxieties that could feel overwhelming in daily life were, in the grander scheme, temporary and small. This wasn't nihilism or a devaluation of human experience. Rather, it was a recognition that perspective matters, that zooming out could provide relief from excessive focus on immediate concerns. Astronomy offered this gift naturally, simply through revealing how vast and ancient the universe was. 3I/ATLAS, in its silent passage through our solar system, had reinforced this perspective for those paying attention. There was also the question of cosmic community. Earth wasn't isolated. Material moved between star systems. Chemical elements created in stellar interiors were dispersed when stars died, becoming part of new generations of stars and planets. Everything on Earth, including the atoms in human bodies, had once been part of other stellar systems. We were quite literally made of star stuff. Interstellar objects like 3I/ATLAS made this connection more tangible. Here was a physical object from elsewhere in the galaxy, made of the same kinds of materials found on Earth, following the same physical laws, subject to the same chemical processes. The universe wasn't a collection of isolated islands, but an interconnected system, with matter and energy constantly flowing between different locations. We were part of that system, connected to the rest of the galaxy in ways both profound and physical. These philosophical reflections didn't lead to publishable papers or concrete results, but they were part of why people became astronomers. The desire to understand the cosmos wasn't purely intellectual or practical. It was also spiritual in a non-religious sense, about finding meaning and connection, about placing human existence within a larger context. 3. I/ATLAS had provided an opportunity for such reflection, and that opportunity was as valuable as any scientific result. The experience with 3I/ATLAS informed preparations for future interstellar object detections. Lessons learned during the observation campaign were documented. Protocols refined, capabilities improved. The goal was to be ready when the next visitor appeared, to maximize scientific return while minimizing confusion and inefficiency. One lesson concerned early detection. 3 I/ATLAS had been discovered several months before perihelion, providing adequate time for observation planning, but not as much lead time as would have been ideal. Earlier detection would allow more comprehensive characterization, particularly of how the object changed as it approached the Sun. This emphasized the importance of continued investment in survey capabilities, particularly systems that could detect faint, fast-moving objects at greater distances. The Vera C. Rubin Observatory, scheduled to begin operation soon, represented a major advance in this direction. Its large aperture and wide field of view would allow it to scan the entire visible sky every few nights, detecting objects much fainter than current systems could find. Simulations suggested it might detect dozens of interstellar objects per year, transforming the field from studying rare events to building comprehensive statistics. But detection was only the first step. Once an object was identified, rapid characterization required coordinated response from multiple facilities. During the 3I/ATLAS campaign, this coordination had sometimes been improvised. Successful but not always efficient. Moving forward, there were efforts to formalize response protocols, creating networks of telescopes committed to rapid follow-up of interesting detections. These networks would include both professional observatories and advanced amateur facilities. The democratization of astronomical capability meant that amateurs with moderate-sized telescopes and digital cameras could contribute meaningful observations. During the 3I/ATLAS campaign, several amateur astronomers had provided valuable data, particularly for monitoring brightness variations that required frequent observations over extended periods. Another lesson concerned data sharing. The most productive research had occurred when data was shared rapidly and openly, allowing different teams to analyze the same observations from different perspectives. But there were also concerns about ensuring proper credit, about not being keyed by competitors who might publish first using someone else's data. Finding the right balance between openness and protecting legitimate interests was an ongoing challenge. Some proposed establishing central archives where all interstellar object data would be deposited and made immediately available. Others suggested embargo periods, allowing discovery teams time to analyze their data before opening it to the community. The discussion continued, trying to find mechanisms that served both scientific progress and individual career interests. Theoretical work was also ongoing, developing better models for interpreting observations. The unexpected properties of 3I/ATLAS had revealed gaps in existing models, places where assumptions about composition or structure didn't match reality. Filling these gaps would improve characterization of future objects, allowing more accurate interpretation of limited data. Young researchers like Dr. Singh were incorporating lessons from 3I/ATLAS into their careers. She was developing algorithms to identify likely interstellar objects from survey data, reducing the time between detection and confirmation. She was also working on statistical methods to infer population characteristics from limited samples, trying to answer questions about how many interstellar objects existed and what variety they showed. Technology development focused on capabilities that would be particularly valuable for future observations. New spectrographs with higher sensitivity could detect fainter spectral lines, revealing more about composition. Improved adaptive optic systems could compensate better for atmospheric distortion, providing sharper images. Space-based observatories, above the atmosphere entirely, could observe wavelengths that didn't penetrate to ground level. There was even discussion of more ambitious concepts. Could a spacecraft be prepared in advance, ready to launch rapidly when an interstellar object was detected? The technical challenges were formidable. Trajectory calculations would need to be done quickly. The spacecraft would need to be capable of high acceleration, and there might be only a brief window when such a mission was feasible. But preliminary studies suggested it might be possible, given sufficient preparation and resources. The infrastructure being built, both physical and organisational, would serve astronomy more broadly, not just for interstellar objects. Better survey capabilities would discover more asteroids, comets, variable stars, supernovae. Improved coordination would benefit rapid response to any transient phenomenon. Advanced instruments would enable research across multiple fields. The investment in studying interstellar visitors paid dividends across the entire discipline. As these preparations proceeded, there was a sense of readiness mixed with anticipation. The next interstellar object could appear at any time, tomorrow or months from now. When it did, the community would be ready, equipped with tools and experience, prepared to learn whatever lessons this new visitor might bring, and each subsequent detection would refine the understanding, building toward comprehensive knowledge of what travelled between stars and what that revealed about the galaxy we inhabit. In the end, what remained after the observations concluded, the papers published, the data archived, was something quieter and more enduring than the initial excitement of discovery. It was an understanding, a slight but real expansion of human knowledge about the universe we inhabit. 3I/ATLAS had come and gone, but the insights it provided would persist indefinitely, woven into the growing tapestry of astronomical understanding. The understanding had multiple layers. At the most basic level, there was now confirmation that interstellar objects were relatively common, that they showed significant diversity in properties and behaviour, that they could be detected and studied with current technology. This established interstellar object science as a viable field, rather than a curiosity dependent on rare, lucky detections. At a deeper level, there was understanding about planetary system evolution. The existence of objects like 3I/ATLAS proved that ejection processes were common, that star systems exchange material with each other through interstellar space, that the galaxy was more interconnected than might otherwise be assumed. This had implications for theories of planetary formation, for understanding of the galactic environment, for consideration of how material spread through the cosmos. There was also understanding about diversity. Not all planetary systems were like ours. Not all comets looked like solar system comets. The variations in composition, structure and behaviour revealed by interstellar objects expanded the known range of possibilities, challenging astronomers to develop more flexible models that could accommodate observed variety rather than assuming universal patterns. This expansion of understanding wasn't dramatic or revolutionary. It didn't overturn established theories or require fundamentally new physics. Instead, it added nuance and detail to existing frameworks, showing that reality was richer and more complex than simplified models suggested. This was how most scientific progress occurred, through accumulation of details rather than sudden revelations. For the individuals involved, there was professional understanding too. They had learned how to coordinate large-scale observation campaigns, how to share data effectively, how to balance rapid publication with thorough analysis. These were skills that would serve them throughout their careers, applicable to future discoveries and challenges. The experience with 3I/ATLAS had been educational in ways that transcended the specific scientific results. But perhaps the deepest understanding was personal and philosophical. those who studied 3I/ATLAS had engaged with something authentically cosmic, an object from beyond our solar system, travelling through space for millions of years before its brief passage through human awareness. This engagement reinforced a sense of connection to the larger universe, a feeling that human existence, however fleeting, was part of something vast and ancient and worthy of wonder. Doctor. Chen, months after the last observation, still found herself occasionally thinking about that faint point of light she had observed through the telescope. It was gone now, continuing its journey through the galaxy, but the memory remained. She had witnessed something remarkable, had contributed to understanding it, had been part of a community united in curiosity and wonder. That experience would stay with her, informing how she approached future work and thought about her place in the cosmos. The understanding also extended to what was still unknown. 3I/ATLAS had answered some questions while raising others. Why was its composition slightly unusual? What specific event had ejected it from its home system? Would it ever be captured by another star, or would it wander forever? These questions might never be answered definitively, and that uncertainty was part of the richness of the experience. Science doesn't provide complete answers or final understanding. It offers provisional knowledge, subject to revision as new data emerges, always open to refinement and correction. The understanding gained from 3I/ATLAS was in this category the best current interpretation of observations, confident but not absolute, valuable but not final. This tentative quality was appropriate for a discipline dealing with phenomena far beyond direct human experience. As time passed, 3I/ATLAS would take its place in the catalogue of known interstellar objects, one entry among what would eventually be many. Future astronomers might reference it in papers, use it as a comparison for newly discovered objects, incorporate its data into meta-analysis examining broader patterns. It would become part of the permanent record, a small but real contribution to human knowledge. The understanding that emerged from studying 3I/ATLAS was, in the end, both humbling and elevating. Humbling because it revealed how much remained unknown, how limited human direct experience of the galaxy was, how vast the cosmos was compared to our tiny sphere of influence. Elevating because it showed that human intelligence, however limited, was capable of understanding phenomena occurring at scales far beyond immediate perception. We could study an object from light years away, determine its composition and origin, place it in context, extract meaning from its brief passage through our awareness. This balance of humility and achievement, of accepting limitations while celebrating capabilities, captured something essential about the scientific endeavour. It was a quest for understanding undertaken with both confidence and appropriate modesty, recognising that knowledge was valuable while acknowledging that complete understanding might be forever beyond reach. 3I/ATLAS, in its silent passage, had reinforced this balanced perspective, offering both answers and mysteries, both confirmation and surprise, both knowledge and wonder. And so we come to the end of our journey together through the story of 3I/ATLAS. This visitor from beyond that captured attention, generated mystery and ultimately expanded our understanding of the galaxy we inhabit. We've travelled together for more than 2 hours now, exploring what it means for an object to come from another star system, what scientists learned from careful observation, and what deeper significance such discoveries might hold. From the initial detection by the Atlas survey, through the intensive observation campaign during perihelion passage, to the careful analysis that followed and the preparations for future discoveries, we've traced the full arc of this encounter between human curiosity and cosmic phenomenon. Along the way, we've considered not just the science but the people who do science, the questions that have no empirical answers but are worth asking nonetheless, and the quiet understanding that emerges when we take time to contemplate our place in something vast and ancient. The answer to the question that might have brought you here, whether 3I/ATLAS represented something that should keep scientists awake, is both simpler and more complex than sensational headlines might suggest. It wasn't dangerous or threatening. It didn't challenge the fundamental laws of physics or require revolutionary new theories. What it did was something more subtle and perhaps more valuable. It revealed diversity where uniformity might have been expected, mystery where everything might have seemed explained, connection where isolation might have been assumed. If you found value in this slow drift through science and wonder, I'm grateful for your presence here. These long-form explorations depend on viewers like you who seek knowledge and peace in equal measure. A like or subscribe helps others find these calm journeys through cosmic questions. And to those who've been here before, who return to let these gentle explorations guide you towards sleep, thank you. Your continued presence creates a community of curious minds seeking understanding and rest in the vast darkness of night. Wherever you are in the world right now, whatever time it is in your corner of this small planet, I hope you're comfortable. I hope your breathing has slowed to a gentle rhythm. I hope the concerns of the day have receded, at least temporarily, into background awareness. I hope your body feels heavy and warm, ready for the rest it needs and deserves. If you can, look up at the night sky, if it's visible from where you are, or imagine it if it's not, that vast black expanse scattered with countless points of light. All those stars, hundreds of billions of them just in our galaxy alone, each potentially hosting planets, most of those planets likely having their own comets and asteroids, some fraction of those objects being ejected into interstellar space, where they wander for millions of years before perhaps, just perhaps, passing near another star and being briefly illuminated, briefly observed, briefly understood. And we are here, on this small world, capable of understanding these processes, of detecting these wanderers, of reading the messages they carry in their composition and trajectory. We're connected to those distant stars through the same physics and chemistry, through the exchange of material that happens when objects travel between systems, through the shared history of a galaxy that has been evolving for more than 13 billion years. There's something deeply peaceful in this understanding. We're not isolated or alone. We're part of something incomprehensibly vast, connected through time and space to places we'll never directly visit, but can still, in some way, know. The journey of 3I/ATLAS, from its formation around another star, through its ejection and long transit through interstellar space, to its brief passage through our solar system, that journey connects there to here, then to now distant familiar. And in understanding this, in taking the time to carefully observe and thoughtfully interpret, in building the knowledge that emerges from patient attention, we honour both the cosmos and our own nature as curious, wondering beings. Sleep well, knowing that the universe is vast and mysterious but also knowable. Dream of ancient wanderers between stars, carrying stories written in starlight and time. Rest in the knowledge that tomorrow there will be more to discover, more to understand, more connections to trace between here and there, between us and the cosmos we inhabit. Good night.